So favorite start for today and for other times. So there was a problem number 29 in the exercise 29. I recommended you to distribute, to rewrite this as a negative 2x squared. That's what we get when multiply the largest powers of x. Then when we multiply first power of x, it'll be 5. The one on the, actually that'd be the numbers. So what's gonna be for the powers of x is x times 1 and then 2x times 5, right? So it's minus 10 and 1 is negative 9x. And finally, the number is going to be negative 10. So this is what we get to find a limit when x approaches to infinity. I believe that's what the exercise was asking to do. Well, and then I can see that this term goes to infinity, therefore everything goes to infinity with a sign negative because of minus 2. I wasn't picking on that minus sign, but to be precise, it's negative infinity plus if you decide to send your x to negative infinity, it'd be the same result, because if you have square of that big number with a minus sign, it's still positive, but negative 2 in front also negates and gives us a minus as a result. So these things one should definitely pay a little attention to. As I said, I didn't downgrade anyone if you put a plus infinity, but it is minus infinity. So it is good idea to think over it again over weekend, right? So how can I think over it? Well, just try to put some big numbers, like 1,000, for example, and you see it's going to be what kind of answer you get. So limits when x approaches to infinity. These things we will encounter in the future, so I decided to devote a little time to this. And we worked on chapter 2, time before last. And we actually observed a special formula that we practiced on, and we're also going to practice more and more on it, because I hope that flavor of derivative will stay with us from now and on. In fact, next couple of chapters deal with derivatives, and we're going to see why we need them, and we're going to find more and more of them. So 2.1 is a section that I was working on time before last, and I'd like to move on to more derivative findings, because what I try to do is to boil this down to use of formula rather than to approach of calculus 1, where they actually give you idea of so-called rates of change, and that's something that brings us to use this type of a formula, but I don't really try to get into that much because it's making things a little bit, I guess, more challenging. So my goal is to see how we can apply all that to the problem solving and maybe real life situations, and that's why I guess we don't really pay much attention on this. So we did a little bit of section 2.1, and today I'd like to extend that process. So we had a couple of formulas, such as n's power derivative was n multiplied by power of n minus 1. That also told us that the constant had a derivative 0, So any number, 2, 10, 17, negative 1/2, they all have same derivative, it's 0. Derivative of x is equal to 1. That's another interesting thing to observe. So let me try an exercise here. Let's say, how about problem number 9? That gives us function g of t function, and I can prepare it as a 2 multiplied by t to the power of negative first. So when I take its derivative, g prime, that factor of 2 will stay. And according to the formula, the power -1 is going to be multiplied by t raised to the power of -1 subtract another 1, right? Because we subtract 1 from the power, and this be -2 to the power of t. So I can write this as a negative. 2 is on the top and t squared is on the bottom. Because we never leave t to the power of -2. We bring it to denominators. Now, there is one more piece of data given here. They also say that t is equal to 1/2, which means that I need to find the derivative at 1/2. In other words, just plug this number 1/2 in our fraction instead of t somehow like that. So they tell me plug it in, so I plug it in. And let's see what we're gonna get. -2, and a square of 1/2 is 1/4, right? So advice is use this denominator, which is 4, and times by it on the top and the bottom. I guess that's the fastest way to deal with these so-called complex fractions. So the answer is going to be with a minus sign. The 4 cancels, and we get 8. So I produced derivative to that function at 1/2. So it turns out derivative is also having so-called physical meaning, and that's a rate of change. In other words, if your car goes to someplace at a rate of, let's say, 10 miles an hour, then the way the position of the car changes every hour is 10 miles. So that's a rate of change of the position. That's the meaning of derivative in physics, physical meaning, rate of change. I don't want to pick on that much, but I guess if you hear it once and then later once again, you'll start to probably feel better about this. So they want to compute various derivatives here. And I'd like to introduce you with another little formula here. In exercise 21, they actually asked to look at the function 2 times square root of x. So it turns out that square root is something that appears every once in a while. So if I need to find its derivative, the 2 is still going to be multiplied by 1/2 square roots. So that's something that I use as a formula. So derivative of a square root is 1/2 square roots of x. So if I use this formula with exercise 21, that I just take derivative of square root and put it as a 1/2 square roots, and we can cancel and get the answer as 1/radical x. Of course, the question is why this is working, and the answer will be given by using that favorite power rule for derivatives once again. So if you decide to do that, if you write this as a 1/2 power of x, right, square root is 1/2. I can do it once, so I don't have to do it all the time, because otherwise it'd be every time same thing. So 1/2 goes on the ground, and x will be raised to the power of 1/2 minus 1. Right? We subtract 1 according to the formula. Whatever the power is, we subtract 1. And this gives us negative 1/2. Because we subtract bigger numbers, so it's negative, and it's a half. So I could bring this power down. So I have x to the power of 1/2 in denominator. And this is nothing else but the square root. So it's 2 times square root x. So what I did, I just memorized this result, but you don't have to always memorize it. You could just produce it every time if you like, but I would memorize it. So there is one more piece of information, just like in a previous exercise, and I'm doing exercise number 21, actually, I should be careful. They say that C is 4. Fine, let's plug 4 instead of x and simplify. So it's 1 over square root of 4. So it's half. That's the answer. So we found derivative, and then we plugged number in it. And again, what is that we found? They say it's a tangent line slope. So if you remember the way the graph of square root function looks like, it's like that somehow. Then at point x equal to 4, someplace here, we can find the tangent line to this function. Tangent line is a line that touches our graph. So its slope of that line is positive, right? And we just found it is equal to 1/2. Please notice that slopes change, depends on this point. The slopes are not going to be the same. But when we have x equal to 4, it's a half. That's what we found. That's really all it is. So we are able to find slopes of tangent lines. That's what derivative actually stands for, turns out. Slope of the line. And, well, I guess we're gonna get used to this little by little. This section is pretty much over, but that's not the end of the story. There is more, of course, in the next section. So let me move on. So techniques of differentiations, and that's exactly where they actually give us these formulas. And I guess I'll just do more derivatives now, just for practice sake. So let's get some problems at the end, because they don't really tell us much difference, but they just want us to practice. So let us practice. Differentiate given function. So let's start with exercise number 1. So now I'm at section 2.2. It says a function is a constant. What will be derivative of that function? Well, the property of derivative says that if it's a constant, then its derivative is 0. It's not surprising, just like we already saw before. How about exercise number 8 with a negative power involved? Well, it doesn't really matter. Positive or negative power, all you do is just subtract 1 from it, right? So 4, and then there's a x power of negative 1.2. Okay, so I take derivative of 4, and that's going to be 0. Again, because it's a constant, doesn't matter. It's 4 or -2, whatever it is. Now I need to take the derivative of power of x. I think I better give it a little room so we don't have to try to fit all that here, this little piece on the bottom, right? So better. That's where you actually start making mistakes, when you start to save paper. So you don't want to save paper, you want to give it plenty of room. So for exercise 8, when I try to find y prime, so we already know that first piece was 0, and then the minus sign. So now this power is going to be my constant multiplied by summation with base x, and that summation is subtraction from the power I used to have, which is minus 1.2, another one, right? So this is going to be the power. So we end up with 1.2 x raised to the power of negative 2.2. And as we don't like negative powers, I'm going to bring this down and write it as x to the power of positive 2.2. I say, Alex, could I leave it like that? You could, doesn't matter to me, but still, it's good to realize that we usually try to turn powers into positives. And then I guess we're done. Nothing they ask us to do with this. How about 27? Let's see, there is a hint in here. Well, their hint is to separate this into pieces. So to have y as a difference of two different functions. So one is x to the fifth divided by x cubed minus, and there is a 4x to the second divided by x cubed. The reason I do this is because now I can take derivative of each piece separately. First piece is x squared, that's my favorite. And the second piece I can write as 4 times x power of -1. Please notice I prepared this as a powers because that's the only way I can take my derivative, because all I have is a power rule for derivatives. So when you differentiate this stuff, the 2 goes down on the ground and power of x will be 1, right? Because all we do is we subtract 1 from the power. So if power is 2, I subtract 1. That's how I get 1. Same with the other one. So -4 is still here. So -1 is going to be multiplied by, and x is raised to the power of -1 minus another one, -2. So let's write the answer. It's 2x. 2 minuses give us a plus. 4 stays, and x squared is on the bottom. X squared is on the bottom. I say, why did you have to do all that? Couldn't you just take a derivative of that fraction right away? The answer is no, because we don't have a formula for derivatives of fractions. We will see that formula, but we'll try to avoid it by all means, because that'd be one tedious formula. Our goal is to learn how to do problems simpler, because the simpler you go, the less chance you make a mistake. That's why the simpler, the better. And to make it look simpler, what I want is to simplify my expressions first. So these groups of problems, they very similar. So they just keep on doing derivatives and more and more. So let me do 33. That's another exercise I'd like to simplify before I'm going to do derivative, because there are 2 parentheses multiplied here. So what I'm going to do is I'm going to multiply the largest powers here. So it'd be x squared times 2x, which is x cubed. What I want to do is put the largest power, x cubed, then x squared I produce by multiplying x squared by 3 here, so that'd be plus 3x squared, of course. And there is another x squared term produced. If I multiply 2x by x, so that'd be negative 2x squared. See that? So we usually arrange powers. First is cube, then is squared, and finally the last will be negative number 3, actually negative x by positive 3, so it's minus 3x. So let me write this again. 2x cubed, because I want to take its derivative, plus x squared, right? And then finally minus 3x. So let's differentiate. So Alex, you say find derivative, now you say the word differentiate. Isn't that the same thing? The answer is yes, it is the same thing. For some reason, they like historically to say find derivative. Sometimes they say differentiate. That's the same thing. Or you can just put a prime. So what do we get? Looks like the formula, and that's what we gonna get here. So let's see, you say that you made some mistake. Let me double check when I distribute. So first I multiply x squared by 2x, so it'll be 2x cubed. Yeah, that one is good. Then x squared, so the red ones, times 3 is 3x squared, and minus x times 2x is minus 2x squared. So this is going to be 3 minus 2 is 1. Okay. And finally, the inside part, minus x plus 3 is minus 3x. Oh, this time I did it right. This time I did it right, but thanks for double checking. So anyways, take a derivative. So 3 goes with 2 gets 6, and then power of x is 2, right? Once more. Next, x squared, so I put a 2, and then x will be in the first power. And finally, minus 3x gives me just x, because derivative of x is 1, so that x simply disappeared. And that feels good. And now they want us to plug in the number. So what they want is the equation of the line. That assumption is a little different because we need to use the formula for line equation. And to get the line equation formula, I need to have a nice friend, the rattlesnake in my backyard. He always tells me that. So it's actually slope. That's what that rattlesnake probably means. One mathematical rattlesnake. But you better watch out because you never know what he means. Sometimes he's not in his best moods. So, well, I guess I need to wear boots and that be fine. So anyways, looks like if you take a derivative, then you need to deal with a point coordinates -1 and 2. So looks like we're going to put a -1 instead of x. You see, I say where do I put 2? Well, later. So we're going to put -1 here, so it'd be 6 -1 squared. So I'm using this new freshly produced formula and plugging in number because this is going to give us slope. So it's 6 minus 2 and minus 3. It is 1. So it turns out the slope, remember we used to get that slope of tangent line, and this is some kind of cubic parabola probably at the point -1. So if I just imagine what's happening here. approximately. Then I have a line with a slope 1. And it also has to pass through the point they gave us. Remember, they gave us point, -1, 2. So what I need is line equation. So I already have a slope. I have a point. I need the line. And to get line, we use this y minus y1 is equal to slope times x minus x1. At least that's getting a little bit too much. I know. Let's just do this one. I guess that'd be good enough because this is a very popular kind of question this textbook has. So they really like to find the slope, and then at the end of the day, use this equation to produce line. So they call this x1, y1. So instead of y1, I use 2. Right, so 2 here. And instead of x1, I use -1. And I also have 1 instead of slope. So you can have like x minus and then x1. So the point is, this is a formula that you probably used a while ago. And this is formula for equation of line. That's what they want. Equation of line or line equation. That's the idea. And we already have it. I just need to simplify this a little bit. So it'd be just x plus 1 on the right side because times 1 means nothing. And also 2 is what I have to bring over to the other side. So I just add 2 and we're done. Add 2 on both sides. So we got a y is equal to x plus 3. So that's equation of that tangent line. So you can see if you decide to get the tangent line, equation will be there. It's a very popular in physics and science classes where they expect you to find some tangent lines. You will see this again among the exercises in the textbook. So every once in a while, I will be just doing it like that. Now, I really want to make you happy. I want to make you happy by giving you a very nice quiz exercise, because I already did exercise 2, and I thought, why don't I ask my students exercise? So I did 1, and if I ask you to do 2 for a quiz, I'm sure you're going to enjoy this a lot, especially because it goes under the formula derivative of constant is equal to 0. I'm sure you're going to like that, right? So can you please find derivative of function y, and that'll be our little quiz for today. And if you forgot, well, I did exercise number 1. The answer will be pretty much the same. And that'll be our little quiz for today. I think that's probably the nicest exercise I can give you to cheer you up a little bit before the weekend, because the weekend is coming. And
Hello, am I speaking to Mauricio Service? All right, look, we can get you that Honda Civic.
Oh, okay, I just muted. So anyways, we got this exercise. In fact, you probably noticed that for quizzes, I don't select the hardest, right? So my goal is just make sure that you see this and that you can put your hands on it, and that makes you feel comfortable. And that's the whole point of calculus. You need to be comfortable with calculus, and then you can do just about anything with it. That's the idea. So looks like people are already answering it. That's great. And when you're done, you can log out and enjoy the rest of the day and enjoy the weekend that is coming. So I'm gonna see you again next week on Monday on Zoom, right? So have a great weekend and enjoy. That's the main thing. Bye-bye.
Thank you, Professor.
Thank you. Thank you for coming. Bye-bye.
Just question number 2, correct?
Number
The
2.
quiz?
Exactly. Yes.
Okay, thank you.
Mhm. Bye-bye. So far, yeah, you see there's nice answers. Nice means correct. Right? Make me happy when we see a nice answer.